So in the previous two videos, we talked about k-fold cross-validation for model evaluation, and then we looked at some code examples for that. And now we are taking a look at k-fold cross-validation for model selection. So the focus will be now on model selection. And that is, I would argue, the more common case for using k-fold cross-validation, because that's usually when we tune the hyperparameters and select the best performing hyperparameter setting, which is something we almost always do in practice, because almost every machine learning algorithm has some settings that we want to tune. So how does it work? So here's a big picture overview of the 5 steps. So I try to summarize it in 5 steps, but I realize it's a little bit small here on that slide. So no worries, in the next 2 slides I will zoom into subsections of that so we can discuss that in more detail. But just to take a look at the big picture overview of these 5 steps. So this is actually very similar to what we talked about when we talked about the threefold holdout method for model selection. So the first step is the same as before. We split the data into training and test set, and then only the step 2 is really new compared to the threefold holdout method. So the not threefold, we call it three-way holdout method, and that is the only new part is that one, because we now replace the validation set with k-fold cross-validation. I will show you or explain that in the next slide in more detail. And then step 3, 4, and 5 is very similar to what we have done there. Okay, so like I said, let's zoom in to discuss this a little bit better, because that's easier to see now, I hope. So in step 1, we do the usual step by splitting the data set into a training and a test set. So we are just splitting it. Now we are only working with a training set for now in these two additional steps. So what we do is, for each hyperparameter setting, we apply then the learning algorithm with a hyperparameter setting with k-fold cross-validation. Now the hyperparameter setting, think of case. I don't want to pick a k nearest neighbors now, because there's also a k and it can be confusing. So let's consider the max depth of a decision tree algorithm. So we can set the max depth maybe to, let's say, 3 or 5 or none, where none means no restriction on the maximum depth. So as long as the algorithm keeps splitting. So, and for each setting we would apply then k-fold cross-validation. We could, for example, use k-fold cross-validation with k equals 10, like recommended by Ron Kohavi, because that's a good trade-off between bias and variance for the k-fold cross-validation estimator. Now, when we do that, we get then the different performance estimates. So each performance here, that's the average performance over the validation folds. So here the performance is averaging over the validation folds. So this will be a single number. And if you think back of the three-way holdout method, what we were doing is essentially the same. Instead of using k-fold cross-validation, we used a validation set. So we had a single validation set, and then got also a single performance value. Now we have the average over these validation folds. Now, after we've done that, after we have done step 2, we can select the best performing model from that. For example, it could be that we find that a max depth of 5 performs best, so we would then select this value here as the best hyperparameter setting, and then we would fit a model to the training data using this best hyperparameter value. For example, the max depth of 5 that we found in the previous round, in round 2 here. So why do we have to fit the model again to the training set? So that's because when we do this whole procedure in step 2, we would have multiple models, right? So if you consider the case that I circled here, there would be one model here, another model here, another model here, and so forth. If we have k equals 10, we would have 10 models. So which one should we pick, right? So in that case, we would just pick the best setting and then fit a model to the whole training set again. In three-way holdout methods, what we did is we merged the validation with the training data, but now we didn't even split. So in the three-way holdout method, we actually split this data into smaller sets in the validation set and the training set, and then in step 3 you merge them back together. Here we don't have to merge anything back together, we can just leave it as is. But yeah, we have to fit the model, because otherwise which model would we pick, right? So yeah, so after we've done that, after we have step 3, we now assume we have the best performing model here from round 2. And yeah, then we can evaluate the model on an independent test set. So now, if I go back one step, we can use this test set here that we had to compute or estimate the generalization performance of this model. So after we've done that, here's the optional step again, where we can fit the model with the best hyperparameter values on the whole data set, because if you think back of the learning curves, we assume that a model might perform better if we fit it to more data. But yeah, going back to this point here, so why do we still have to have an independent test set? Yeah, it can be just because of the selection bias that we could have when we pick, if we pick a case just using k-fold cross-validation. So we could just by chance find a hyperparameter that just performs well on k-fold cross-validation. So maybe our estimate is also slightly optimistic, because we use k-fold cross-validation, the same splits over and over here. So actually it's quite robust to overfitting, so k-fold cross-validation is quite robust, but still, if you can afford it and set aside some independent test data, this is always preferred. So you can have still, in step 4 here, this independent test set. Okay, so and this procedure is k-fold cross-validation for model selection in a nutshell. Yeah, now let's take a look at some techniques for selecting hyperparameters for the model selection or hyperparameter tuning step. So one common method is grid search. I would say that's still the most widely used method. It's an exhaustive search method. So how that works is you define a list of hyperparameter values. If you have only one hyperparameter to consider, if you have two hyperparameters, you consider a two-dimensional grid. If you have 3, you will specify a 3-dimensional grid, and so forth. So let's take a look at an example, maybe because it's simplest, k nearest neighbors. So for example, you can tune k, the value of k. Let's say we have k equals, 3, 5, 6, 7. We can also include a 4, 5, 6, 7, 8, 9. So we have these values that we want to consider for k. So if we only have one hyperparameter to consider, this would be a list. We just, by brute force, or not brute force, but exhaustively, we just run the algorithm with each setting and then compare the performance with k-fold cross-validation. What's nice about it is we can run that in parallel, right? So we can run on, if we have 1, 2, 3, if we have 7 processors, we can run all of them at the same time. We don't have to wait until our KNN with k equals 3 finishes before we run k equals 4 and so forth. Now if we have a second hyperparameter, for example, think of the p and the Minkowski distance definition. So we have p, for example, let's say 1, which is the Manhattan distance. We can actually just write it explicitly. Manhattan distance and Euclidean distance. So this would be then our hyperparameter grid. So this would be a grid where we have 14 hyperparameter combinations, and for each of them we would get the performance with k-fold cross-validation. So doing that with considering all values of k and the different distance measures, it would be a thorough but expensive way to do hyperparameter combinations or selections. So here we only have 14, so here it's of course cheap, but now think about expanding k and adding more hyperparameters. So in this case of k nearest neighbors, it's actually quite simple. It's not that expensive. For certain algorithms that have a lot of settings, that can become easily very expensive, especially for those students who took statistics 453 in the context of deep learning. We have a lot of hyperparameters to tune. Yeah, so how that works is, in general, we have to specify the grid, like described above. If we had a third hyperparameter, we would actually make this a cube, so hypercube, 3-dimensional, so we would have another hyperparameter around the z-axis and so forth. Yeah, one problem with that is it can suffer from poor coverage. So usually that's not an issue if we have these discrete values. However, if we have continuous values, or if we would skip some of the k values here, that could be a problem. So for example, in gradient boosting, think of the learning rate, which is a continuous value. So I can specify, let's say, a list of 0.1, 0.5, and let's say 1.0 is the learning rate. But now we don't cover anything between 0.1 and 0.5, or nothing in between 0.5 and 1.0. So that could be an issue, a coverage issue. So in practice, sometimes people run also grid search multiple times. So for example, let's say you run your grid search and you find a solution with a learning rate of 0.1 performs best. So, but yeah, 0.1, given this list here, is quite a rough estimate, so maybe there's a better learning rate that we haven't considered in this list. So you could run grid search again, for example, with a new list, for example 0.01, 0.05 and so forth, up to 0.5. So all the values, maybe not 0.5, but let's say 0.45, all the values between the range, so all the values between here and maybe even some lower ones that we have not included before. So you can then expand the list and run a finer hyperparameter search on these values. So ignoring everything that is above 0.5, for example, if you found 0.1 performs best. So with that, I mean, you can often run, or often in practice it's done, that you do multiple iterations of grid search with multiple resolutions. So here on the right-hand side is a visualization from a paper by Bergstra and Benjo. So what they did here is, the article is essentially about randomized parameter search, which I will show you in the next slide. But here is a visualization of also the poor coverage issue. So here, imagine there's an important parameter and there is an unimportant parameter. So in that way, when you run grid search, you usually run that sequentially. For example, you may you run these first and then you do it like this. You do it like, unless you shuffle the hyperparameter combinations, which you can totally do, you would run that sequentially. And it may be that if you have a time budget, if you say I only run that many iterations, then you may never reach the last part. But in grid search, it's usually that you run everything exhaustively. However, the coverage issue is that you would never cover anything between these two values if the points represent only the points that you evaluate. So everything here is maybe not considered. So, and if you look at this density plot here, let's say the density represents performance of the model if you choose that particular hyperparameter value. So given this peak here is the, best performing model, this range here, this range of hyperparameter values would be the most important one. If these are continuous hyperparameters, and this one would be an important one, so here it doesn't really matter, but it might be, if you look at this slight peak here, that this intersection here might be giving you the best model. However, if you do a grid search, you may not cover it because the way you define these values are not including that value. For example, like I talked about here with the learning rate, you may choose the intervals such that this is never really sampled. So yeah, randomized search addresses this issue by sampling from distributions. So you can specify a distribution to sample from. You can choose any distribution you like, a uniform, continuous and discrete, of course, if you have a continuous or discrete hyperparameter values, but also You can use a normal distribution, exponential, beta distribution, whatever you like, binomial. So in that way, you have a wider variety of values you can explore compared to just specifying the grid yourself. And usually in practice, the search is done based on a time budget. So you say either run randomized search for 100 minutes, so some implementation support that, or you can say run that for a given number of iterations. For example, that's done in scikit-learn. I will also show you a code example in the next video, so you know how you can do that in practice with a number of iterations. And yeah, this is usually preferred if you have many hyperparameters to consider, for example, more than 3. If you have maybe 2 or 3, it's maybe not worth it. You can actually define a fine grid and use a regular grid search. But if you have more than 3 hyperparameters that you want to tune, I think using randomized search is actually a good idea. So like I said, you can specify a distribution for the parameter search, and I think that will also become more clear when I show you the code example. And similar to grid search, it can be run in parallel. There are some other hyperparameter optimization techniques, for example, Bayesian optimization, but we won't talk about that. I think it's less common in practice also because it's sequential, and that can be more expensive because Bayesian optimization you have to run in a sequence, and really I think in practice it's not that useful compared to doing randomized search. So here is again the same illustration of grid search from the previous slide. On the right hand side is the randomized search layout. So here we would randomly sample hyperparameters from the distribution. So just by chance it might be that we include some parameters from here randomly. So here this would be exploring the space randomly by sampling from random distributions. So here you would have actually a chance to sample from this range, where here it might be that you fail to specify a value between those two values. So in that way, on the left hand side we would suffer from the poor coverage problem, whereas on the right hand side we might sample a value from there. But of course this also requires that we set a high enough number of iterations or candidates to evaluate. Okay, so in the next video I will then show you how we can do that in practice.